Here's a rigid body kinematics question that can actually be solved using Euler's formulas as usual, but it turns out it's actually a bit easier if we do it geometrically. So let's see what this is all about. We have uh, point A, which is being given a constant acceleration a to the right, starting from rest, while x was initially 0. Okay, so in other words, basically point A starts from close to where point C is, right? So we're going to assume that point A and point C were mathematically the same at the beginning, right? And then in this case, we're asked to find the angular velocity of bar AB in terms of x and in terms of the acceleration a, and of course in terms of the length of the links, which are both equal to b. So the first thing I would do here is try to find what is the velocity of a as a function of distance and as a function of acceleration as well. So as the acceleration is constant, right, we can then have the velocity being equal to the initial velocity plus a times t. Now, the initial velocity is 0 because a starts from rest, which means that v is equal to a times t. Okay? And this gives us the velocity at a in this moment, except we don't know what the time is. So we have to use another of the Suvet equations to find what the time is. And to do that, we're going to use the displacement. So for that, we have x equals x0 plus u times t plus 1/2 at squared. So this is the general expression for the displacement. Now, in our case, we measure the displacement from C, right? So we place our coordinate system here, right? We measure x in the right direction, and if we measure it from C, then x0 would be 0 because we measure everything from C. This is 0 as well because A starts with 0 initial velocity. So that gives us that x is equal to 1/2 at squared, which means that we can find t squared as 2x over a, like this. So once we know t squared or t, so obviously t is just the square root of 2x over a, and it's positive, so we don't have to worry about the sign. We can now find what v is. So v is therefore a times t, which is a times square root of 2x over a. We can cancel this out, put a square root here, and we end up with the square root of 2xa. Okay, we could have done this a bit more straightforward, but I wanted to show you the step-by-step way of doing it by eliminating time from both equations. Okay, so we know the velocity of point A as a function of distance and acceleration. So let's try to start working out that angular velocity. So I'm going to start this by first looking at point B. Okay, so point B is part of the CB link, which I'm going to draw here. So C is actually fixed. Well, it's not fixed, but it's hinged like this. And C is not going anywhere, which means that C is acting as the center of rotation of the whole CB link, right? And point B is, of course, here. And if you can imagine this, basically what happens is that as point A goes to the right, then CB is going to rotate clockwise, okay? Which means that, oh, by the way, if we used Euler's formulas, we wouldn't even have to make this assumption in the first place. But here we have to think a bit more, use a bit more of our intuition. So CB is going to rotate clockwise, and then point B is going to therefore move in a direction which is perpendicular to the CB length. Okay, so the velocity of B is going to be equal to omega 1 times B. So that's lowercase b, which is the length of the CB link. And omega 1, of course, is the angular velocity of the CB link. And I'm going to call the other angular velocity omega 2. Okay, so this is we haven't really figured out the value of VB because we don't know what omega is, but we know what the direction is, and this is key, as you'll see in a second. So now let's try to look at B, at point B, but from the other side. We're going to look at it from the perspective of the BA link instead. So that one looked like this. So I'm going to draw the CB link. So don't think I'm going to draw the thickness anymore. And then we have BA something like this. Okay, now we know what the direction of the velocity of B is, right? And it's perpendicular to the CB link, so it's going to be something like this, more or less. I'll try to draw it as perpendicular as I can. So this is omega 1b. Okay, now link AB doesn't actually have an obvious center of rotation, right? Because as opposed to CB, where C was hinged, A is not hinged at all because A is also moving by itself. So how can we actually find what's the instantaneous center of rotation? And that's actually what we have to find. That's the key to solve this. We have to find what's the instantaneous center of velocity or the instantaneous center of rotation, which is the same thing. And to do that, we're going to use the fact that B is part of link CB and it's also part of link BA, right? And we know what the velocity, what the direction of the velocity of B is, and it's perpendicular to link CB. So the next thing we have to find is we have to find the direction of the velocity of another point on link AB. And we know that. We know that the velocity of A is pointing to the right? Because A is constrained to move horizontally, and we know it's the acceleration is to the right, and A has been moving since x was 0, so we can safely say that the velocity of A is like this. And we know what that velocity is as well, right? That velocity is the square root of 2, all right, 2ax. Okay, so once we find the directions of the velocities at B and A, we can find what the instantaneous center of rotation is in a very simple way. So from each velocity, we are going to draw a perpendicular to that velocity like this. So this is this green line is perpendicular to VB, and this green line is perpendicular to the velocity at A. More or less like this, and this I'm going to call this point O. And in this particular moment, this is the instantaneous center of rotation of link AB. So just in this moment, point O is stationary and B and A are rotating about point O. Okay, and after a few more seconds, there will be another center of rotation, so the location of this will change, which is why this is called the instantaneous center of rotation, right? Because it's only valid for an instant, for a moment. So we can now try to find the angular velocity of AB, right? And here's how we do this. We're going to have to use some geometry for this. Now, I'm going to split this triangle in two, and we're going to look at this right triangle here. Now, this side of the triangle is B, and I'm going to call this angle theta. Okay, we don't really care how much theta is, but we'll call it theta now. And also, I'm going to split this triangle, this green-white triangle in two, where this angle is also going to be 90 degrees. So we can see a few things here. First of all, this angle is equal to this angle. They're both 90 degrees. Then this angle theta is also equal to this angle, which also has to be theta, right? Because this is parallel to this and this is parallel to this, basically. And also this side is equal to this side, right? This side here is x over 2, and this side here is also x over 2 because it's parallel and it's equal to this side, which is x over 2. So we have this angle, and this side equal to this angle, and this side, which means that those two triangles, so this triangle here and this triangle here, are congruent to each other. So all the other sides are also equal to each other, which means that this side is also equal to b. Okay? So let's try to write down the velocity of b given the fact that we know that O is the instantaneous center of rotation. So here's how we do that. We have the velocity of b on one hand is omega 1b, but also vb is given by omega 2. Omega 2 is the angular rotation, is the angular velocity of AB, and this is times b again, right? It's basically the omega of AB multiplied by this b. So what you'll notice is VB is omega 2b and VB is omega 1b, meaning that omega 2 is equal to omega 1. Right? The direction of rotation of the two bars are different, but the magnitude of the angular velocities are the same. So I'm going to call this angular velocity omega 1, omega 2. I'm just going to call it omega. Okay? Right. So the other thing that we can use is the fact that the velocity of A is equal to the angular velocity of AB multiplied by this distance here. Okay? And we can actually find what that is by first finding this side, and we can find that side using Pythagoras. So that side is the square root of b squared minus x over 2 squared. Right, so b is the hypotenuse, x over 2 is one side, which means that the other side has to be equal to this. So let's try to write this here instead. So we have that side as the square root of b squared minus x over 2 squared, which is b squared minus x squared over 4, which turns out to be 1/2 square root of b squared square root of 4b squared minus x squared. Okay, so the whole thing, the whole distance from O to A is twice this, right? Because this distance is equal to this distance, because this triangle here is congruent to the triangle on top of it. So OA is 2 times this, meaning that OA is the square root of 4b squared minus x squared. Okay, so we can then write the velocity of A in terms of the angular velocity and the OA distance. So the velocity of A is equal to omega times OA, which is omega times the square root of 4b squared minus x squared. And we know what VA is from the very first part of the question, right? It's this here. So VA is square root of 2ax, and it's omega times square root of 4b squared minus x squared. So finally we get an expression of omega explicitly, which is the following. Omega equals square root of 2ax divided by square root of 4b squared minus x squared. Yes. And that's it. That's the expression, that's the final expression of angular velocity, and it's purely in terms of things that we know. It's in terms of the acceleration A, in terms of the distance that A traveled, and in terms of the constant B, which is the length of the links, which don't change with respect to time. So the only variable here is x, really, if you keep the acceleration constant, which you have to, because otherwise this velocity is not going to be this anymore. So yeah, that's the end of the question.